So, section 7.2, today we're going to deal with infinite series. So, the first question is, what's the difference between a sequence and a series?
One is added up. Series is added. A sequence added.
Okay, a series is added. So, in a series, you add all of the terms. What is a sequence?
A list.
A sequence is just a set. You could call it a list, I suppose. A list of terms. Now, I mentioned last time in section 7.1 when we were doing sequences, you have to keep these two straight. It is really important for what we're going to be doing in the next 3 or 4 sections that you pay attention when we look at theorems and stuff to make sure that you know whether we are talking about a sequence or a series or how the two are related. And you should have your books open to page 592. 592 starts out with a simple fact. It starts out with the fraction 1/3. And it says, how do you represent 1/3 as a decimal? How do you represent 1/3 as a decimal? This is not a tough question. You all know it from 5th grade. Yeah, it's 0.3 bar, right? Okay, well, let's just expand this a little bit. This is 0.3333333, da da da. Okay, so what does that 3 represent? Yeah, if I write that as a fraction, that's the fraction 3/10. What is that 3?
300.
That's 3/100ths. What's that 3?
3,000.
That's 3/1000. Okay, and for how long do the 3's go on?
Forever.
Okay, that's an infinite series. This is an infinite series because I can express this as 3/10 plus 3/100ths plus 3/1000ths plus 3/10,000ths plus 3/10 to the n plus. So I have an infinite number of terms. And here's the funny thing. This is the part that some people just accept it and it's good, and other people, it messes with their heads and they don't like it. Okay? The fraction 1/3 equals the sum of an infinite number of terms. I have an infinite number of 3's. If I add that infinite number of 3's together, I get exactly the number 1/3. I remember doing this with my teacher. I think I was in 4th grade at the time. And so I said to my teacher, I noticed, I had seen this, I said, well, what's 1/3 plus 2/3? It's just 1. But I knew that 1/3 was 0.3 and 2/3 was 0.6, so I said that equals 0.9. So I went and asked my teacher, I said, this doesn't seem right to me. How can 999999999 forever equal 1? And she said it doesn't. Well, it does. In point of fact, it does. The math here is right. And some years later, I showed this to another teacher, and this was my first algebra teacher I ever had, and she actually explained it this way when I was an 8th grader. She said, what would you add to this number to get 1? Which was a nice intuitive way of describing it. And I said, I don't know, how about this? An infinite number of zeros with the 1 at the end. But you can't say an infinite number of zeros with the 1 at the end because the zeros have to keep going, so there's no end. So you can't put a 1 at the end. So we'll see why, we'll have a formula for these to show why these two things are equal, but these two numbers are actually exactly equal. 0.9 forever and 1 are the same exact number. It's just, this is expressed as an infinite series, and that's not. So if you take a look, one of the things we want to be able to do is we want to be able to add up series. We want to try to figure out, does series converge or diverge? We know some tests for sequences, right? I can have a sequence, we did some of this last time. If I could have a sequence like 1, 1/2, 1/3, 1/4, 1/n. I can talk about whether the sequence converges. How do I determine if the sequence converges? You just take the limit, right? So I'll take the limit as n approaches infinity of 1/n, and it's 0. So we know that the sequence converges. The harder thing that we're going to have to ask ourselves and play with is, does the series converge? If I take this sequence, 1, 2, 3, 4, 5, 1 third, a fourth, a fifth, all the way to 1 over n, and I add that up, does that also converge? If it does, what number does it converge to? Can I tell? If I can't tell what number it does converge to, assuming it does, can I at least put a bound? Can I say, well, it's a rough bound, but at least I know it's not bigger than 10? This is where we're headed. So these two things are related, but they're not the same thing, and so we have to keep our stuff straight. The book starts out after this example. It gives the example at the bottom of the page. Let's see what happens if we add halvesies. So they said, all right, let's do this. And they use an intuitive proof here to start with. They say, let's take a half. We're going to take the sequence 1/2, 1/4, 1/8, 1/16, 1 over 2 to the n. And they say, let's just start adding this and see what happens. So I'm going to take a half and a fourth. What's a half plus a fourth? 3/4, right? Okay, what's a half plus a fourth plus an eighth? 7/8. What's a half plus a fourth plus an eighth plus a 16? What's that? 15/16. That's right. And on it goes. So what the book says is, what is this getting closer and closer to? It's getting closer and closer to 1. And in fact, if you add up all of these infinite number of terms, what do you get? You get exactly 1. So we've played this game before in other classes. They say, who wants to leave? Remember this? They say, who wants to leave the classroom? Okay, mirror 2 gets to leave. Okay, mirror 2, you can leave the classroom, but there's only one rule. You can only go to the halfway to the door with each step. So your first step, you're halfway to the door. The next time you're halfway again, then half again, and half again. And if every second you only go half the distance to the door, there's always some distance left, right? So you get infinitely close to 1, but you never get there. Because you actually can't take an infinite number of steps. You're taking 1 per second. But what if I said, okay, you can take an infinite number of steps. Ready, go. How far do you get? You just get to the door jam, but you still never leave the room. Yes? Now, the book shows this, and it doesn't prove it at this point. It just starts out with this, and it says, how do we know if it's going to converge or not? Well, we can actually prove this, and the way we can prove it is like this. Let's do this. Let's take a half plus a fourth plus an eighth and a 16th, right? How many of you have done computer programming? Have you done any work with binary? Well, just look with me for a minute. Let's just all convert this to 16ths, okay? So I got 1/16. How many is this? 2, right? How many is this? 4. How many is this? Look at this. 1, 2, 4, 8. What are those? Those are the powers of 2 going in reverse order, right? So think about binary. When you're counting in binary, did you say you've done binary or haven't done binary? You haven't done binary. This proof is not going to work so well. I'll show the computer text this later. It's kind of fun, because when you count in binary, you just have on and off. So here's my hand. I'll just count in binary real quick. This is 0. This is 1. So how do I do 2? It's just like when you count in 10. You go 1, 2, 3, 4, 5, 6, 7, 8, 9. What happens when you get to 9? No more digits, so you have to go to 2 digits, right? With binary, you only have 2 digits. There was 0, there's 1. I used my 2 digits, 0 and 1. So what's my next digit? I got to go over here. So I can't, oh, sorry about that. So, always have, so you can't like that. So, at some point you got to get to 4. That's the way it is. So in binary, and when we're doing our work in base 10, this is the 1's digit, this is the 10's digit, this is the 100's digit, right? This is 1, this is 10 to the first power, this is 10 squared, right? And you keep going. In binary, it's 1, 2, 2 squared, 2 cubed, so it goes 1, 2, 4, 8. So if I have this, I have 1 plus 4 plus 2 plus 1. I have 1, 8, 1, 4, 1, 2, and 1, 1. What happens? I'm out of digits, so if I go to the next one, I have to put a 16 here. And what ends up happening with this, if you add this all up, you keep filling up all the digits up here and having to go to the next one. You end up getting infinitely close to 1 with the fractions. Let's do this, because I would prefer to give you a formula now. The book waits a few minutes to develop it. The formula that they're going to develop is over on page 595. I'd rather develop it now to show you why this works. You'll recall from pre-calculus that we had a way of writing this. How did we write this using sigma notation? You write sigma.
Ends on top.
What's that?
Ends on top.
Ends on top. What's down here? I equals 1. So this is going to be 3 over, oops, 10 to the I power, right? Okay, so one of the questions we have, and what kind of series was this called when you have something that's multiplied by the same factor, every term gets multiplied by the same factor? Anyone remember? You had geometric? You had the geometric series. A geometric series is when you multiply each succeeding term by the same exact number, and R is your common ratio. So far, so good? So in this case, what's my common ratio? 1/10 is my common ratio. So, and you can tell that because the power here is on 10. So it goes 2 squared, cubed, fourth, every term you get another 1/10. So the question is, if we have a series, we can write a series like this. My first term we usually call A, or A sub 1. So what would my second term be if I'm using R as my common ratio? It would be AR. It would be A sub 1R plus, what's my next term? It's A sub 1R squared. Why? Because the way a geometric series works, I take the common ratio and I multiply R by every term. So here's my first term, I don't have an R. Then I multiply by R, I multiply by R, I keep multiplying by R, so my series is going to look like this. Now each of these also has a different name. This is my A sub 2 term, this is my A sub 3 term, this is my A sub 4 term. And so we have a nice formula if you just want to find the value of a particular term. If I want to find the value of the A sub nth term, what is the A sub nth term equal to? Yeah, if you take a look, this is the second term, and it's R to the first. This is the third term, but it's R squared, so it's A sub 1, R to the n minus 1.